Let's talk about algebraic equations. Um, Before we can introduce this concept with a little bit more accuracy, we need to understand a few other concepts that are important for it. So the first one is power of x. What is x? X is one unknown that we tend to give it the name x. Obviously, it could be any other letter as long as we agree which one the unknown is. So let's say that for us is x. What is the power of x? It is nothing but the concept of a power between numbers applied to having the base equal x. So if normally I would call this one, for example, a power to power 5, we know that is 32. The concept of power of an unknown means that that unknown is used as a base and the exponent is actually a number. Typically, when we talk about power of x, this number is integer and positive. So in other words, it is x power to n, where n is a number of our old friend, the set of the natural numbers. So what that means is n could be 1, 2, 3, or something like that. So what is a monomial then? Monomial is a concept that is based on the power of x, but there is a bit more to it. So a monomial is not only a power of x, for example, x power 3, but there is a coefficient multiplied to it. And this coefficient could be any real number. So it could be 2, that is a monomial. It could be minus 2, for example, x power, should we say x power 5, that is a valid monomial as well. Another monomial could be square root of 3 times x power 2, for example, or x squared. That is a valid monomial as well. So any real number multiplied by any power of x with the exponent integer positive. In other words, this number here, which in this case is 2, in this case is 5, has to be a natural number, so positive natural number. Just to note that if you have this writing, for example, x power 6, that is also a valid monomial where the coefficient that is not indicated can be assumed to be 1. So if you don't see a coefficient, it means the coefficient is there and it is 1. Why? Because multiplying any number, such as x power 6, by 1 leaves the initial number x power 6 unchanged. So 1 times x power 6 is the same as, or coincides with, 3 lines equal, is the same as x power 6. So these are all valid monomials. What is a polynomial then? A polynomial is an algebraic sum of monomials. So what is an algebraic sum? Algebraic sum means either a sum or a subtraction. Or let's remember that real numbers have their own sign. So essentially adding two numbers, which could be positive or negative anyway, either of them, doesn't really make a big difference, to subtracting numbers, because anyway the sign can be either, as long as we know which one it is. So for example, if I have two monomials, 2x and 5x squared, these are two monomials, each of them, because there is no sign indicated, each of them have got sign plus. So if I do a polynomial, if I build a polynomial based on a sum of these two, I will have 2x plus 5x squared. However, if I consider these monomials, 2x and minus 5x squared, if I now decide to apply an algebraic difference of the first minus the second, I will have 2x minus 5x squared, which is 2x plus 5x squared. So essentially, as you can see, because each monomial has their own sign, having sum or difference, when we talk about algebraic sum, algebraic difference, doesn't actually enhance the number of combinations we may have. Obviously, it gives a different result though, so we have to be careful. Either it's a sum or it's a difference. So Anyway, what is a polynomial then? It's an algebraic sum of a number of monomials. It could be one, so in this case a polynomial is that monomial. For example, if I take this one only, this is a monomial, it is also a polynomial. I'm not adding anything else, it's a polynomial already. This one is a polynomial. I'm taking two monomials, so it's plus 2x added to plus 5x squared. There may be more, actually. There could be 2x minus 1/3 x power 4 plus x power 6, for example. That is a valid polynomial. There is no limit to the number of monomials you may add. An important concept, though, is to consider the maximum exponent of all the monomials that make up this polynomial. So if I look at this one, in this particular case, this is a polynomial of x. It depends on x, so it's a function of x. It's made up of three different monomials. This, and that. Which one has got the highest degree? The degree of x not indicated to any power means it's power 1. So this degree is 1. This degree is 4. This degree is 6. The highest of these degrees, by definition, is the degree of the polynomial. So the degree of a polynomial is defined as max degree of its monomials. So one important concept, obviously, in math is the concept of equation. Equation is an equality between two members, which are many times called left-hand side member and right-hand side member, or first member and second member. And this equality may depend on the value or values taken up by its unknown or unknowns. So a very, very generic equation I can write is some function of some unknowns, let's say x, y, z, maybe others, equal to 0. This is the most generic equation I can think about. Now, there is no generic solution to that because that depends on a number of factors. The most important one is that we don't know what is this function until we know it, until we actually define it. What is this function doing? Is it adding? Is it multiplying? Is it adding and then multiplying? Is it taking a logarithm? Is it taking an exponential? Is it considering a sine or cosine? So obviously it depends on the nature of this function. And also because there are a number of unknowns in this particular case, there might be one, could be only x. There might be two, maybe x and y or x and z. There might be 3, 4, 5, there might be whatever number. Generally speaking, this equation doesn't have one solution, but infinite solutions, if it has any solutions. So if I now limit my scope to a slightly more interesting equation when we talk about seeking solutions, I will consider f of one variable only equals 0. So what's the difference here? In this case, I didn't know how many variables I would have, how many unknowns. In this case, I'm assuming it's only one, it's only x. So that's a little bit more, a little bit more tightly defined. However, we still don't know what is f doing. Is it adding? Is it taking the sine or cosine? Is it calculating a logarithm of x? We don't know that. So do we have a solution for this equation in math that always works? No way, not possible. There may be special cases that have a solution. There may be special categories or classes of cases that have a special solution, and we will look at them. There may be classes of cases that don't have a solution always valid for every possible value of x, but some sort of approximation around some particular value. So in other words, they could have some local solutions maybe. So let's look at the nature of this f now. What is an algebraic equation? An algebraic equation is one where this f is only made of the 4 basic operations that you know since primary school. So that means plus, minus, product or multiplication and division, enhanced by a couple more that are power of. So in other words, for example, this monomial, x power 2, so power, and this power actually can be to any rational number. So what does that mean? If this rational number is also an integer number, you could have monomials now. If this number is a fractional number, so it is rational and is not natural number, for example, power 3/5, this fifth actually becomes a root of index 5. So in other words, if I got 2 power 3/5 is defined in math as root of index 5 of 2 power 3, which we know the content of this root is 8, fine, but that is within a root of index 5. So these operations are still allowed in the definition of algebraic equation. So what that means is, for example, this is an algebraic equation. Square root of x minus 1 divided x plus 1 plus cubic root of x power 2 plus 1 minus 5 equals 0. For example, this is a valid algebraic equation. So question is, okay, now we have a slightly smaller field, smaller scope of equations. Have we got a formula that always works for this type of equations? No, we haven't got one. We have for some cases. So if the equation has got some particular properties, then we have it. But it would be possible even for a very young child to make up an equation of this nature that a senior mathematician could not resolve, or at least he could not resolve in a closed form. That means with a perfect value that is actually accurate and satisfies this equation. There are some particular cases of equations though that work and we can actually find a solution. So this is an algebraic equation, and there are also fractions within this where the unknown is at the denominator, as you can see. That is an additional complexity, by the way. Even if there were no square roots, no roots, square or cubic roots, the fact of having an unknown at the denominator may add a level of complexity, and it usually actually does. So what is a slightly simpler type of equation is a rational algebraic equation. So a rational algebraic equation is one with the same operations as above, with one difference now. The only exponents considered are integer. So I cannot have 3/5 as an exponent. For example, that means I cannot have a root of the unknown. So for example, if I have something like 2x squared plus 1 divided to x minus 3 plus 5x minus 7 divided by 2 equals 0. This is a rational algebraic equation, so there are no roots in this case. Let's be careful though. Roots are allowed here as long as they don't touch the unknown. So if I put a root here, for example, this is no longer a rational algebraic equation. It's an irrational algebraic equation. However, if I put a root here, just taking the square root of 3, for example, this is a rational algebraic equation. So this adjective, rational or irrational, only refers to the unknown. In our case is x. So if we are taking roots of x, that becomes irrational. In this particular case, we are not. So then the question is there again, do we have a formula that always works for this type of equation then? No, we don't. We have nice formulas that work for a number of cases. We have a nice processes that simplify this type of equation sometimes, if the equation is not too complex to start with. And in that case, yes, we can get to a final solution. But generally speaking, I could make up an equation of this form that doesn't have, well, that may well have a number of solutions, but nobody will be able to find them easily. Right. Let's talk about some particular rational algebraic equations that do have a formula then that we can use to resolve them. So if we talk about rational algebraic integer equations, so let's simplify even one step more. So now we talk about integer rational algebraic equation. What's the difference to the above? Now we have an integer equation. Again, this integer does not refer to fraction of numbers such as 1 divided by 2 a half or 1/3. Those numbers are still fine, they're still allowed. What is not allowed in this type of equation is to have the denominator that contains x. So for example, if I have x divided by x plus 1 minus 3 divided by 5 equals 0, this is not an integer rational algebraic equation, it's a fractional rational algebraic equation. However, if I don't have x here, instead of x plus 1, let's say if I have 3, all at once this becomes an integer rational algebraic equation. So in other words, x is only at the numerator of fractions if any fractions are there. It's not at the denominator. X is never inside the root if roots are there. So essentially what it means is now we are really limiting the type of expressions we can write. So essentially this is taking the shape of something multiplied by x is 1/3 multiplied by x, if you want to read it that way, minus something that is a constant term without x in this particular case. Let's make one that is a bit more complicated. So this one, for example, 2x power 7 minus 1/3 x power 4 plus square root of 5 x power 3 minus 2x power 2 plus 99 equal to 0. Is this an integer rational algebraic equation? Yes. It is algebraic because the only operations included with, executed on the variable x are possibly the 4 operations, so plus, minus, multiplication, division, and powers of rational exponents. So it is algebraic. It is rational because all the indexes are integer. So I don't have here 4 divided by 3 or 4 divided by 9. So in other words, x is not inside any root. So it is algebraic, yes. Rational, yes. It is also integer because x is not at any denominator. As you can see, the only denominator I got in this case is 3 here. I could have here, for example, 21. It wouldn't change the things. This is still an integer rational algebraic equation. That calls the question again. Right, okay, so have we got a formula to resolve this that always works for any integer rational algebraic equation? No, unfortunately we don't have one. The complexity of this type of equation essentially sits with this number, or with all the degrees, essentially, with the combination of the degrees. And of course the coefficients have got their own importance as well. So generally speaking, what makes an integer rational algebraic equation potentially complex is the degree of the equation. In other words, the highest degree of all its monomials. So what if we start to make assumptions on this maximum degree and we limit it to something real small and then maybe a bit bigger? Maybe we could get a little bit of luck in there. So let's study integer rational algebraic equations with additional assumptions. So now we are in the field of integer rational algebraic equations, and let's assume the degree is 1. So what does it mean? An integer rational algebraic equation, as we said, has got the shape of a polynomial that depends on x equal to 0. That either it has that shape or you can make it take that shape with simple operations normally. When the degree is 1, it means that this polynomial has got degree 1. So remember, polynomial is made of all the terms from the constant term up until the degree that is the maximum degree we're considering, which is 1. So in other words, this is made only of two possible terms, the one without x and the one with x to power 1. So we could give it this shape, something multiplied by x power 1 plus something not multiplied by any x equal to 0. That is an integer rational algebraic equation with degree 1, also called linear equation. Remember, we're talking about equations in one unknown, there is only x. If there were more than one, if there were 2 or 3, that would have representations in geometry. For example, with 2 it would represent a straight line, with 3 it would represent a plane in 3D and so on. But with one unknown, all we're looking for here is values that satisfy this expression. So the question is, first question is, are there values always or not? Second question is, if there are there more than one? May they be more than one, or is it only one? Could there be infinite values? And the last question obviously is, do we have a formula to actually find those values? And the answers in this case are much more positive, because we are really limiting our scope now to very simple equation. So the answers depend essentially on the value of this coefficient a. So if a is 0, what happens? 0 times x is 0, so this goes away essentially, and I'm left with b equal to 0. So this one could have two possible ramifications. So if b was 0, then it's an identity that takes the shape of 0 equals 0, because 0x plus 0, 0 equals 0. So essentially all possible values of x are a solution. And this is not very interesting, to be honest, in most cases. In some cases it might be. If b is not 0, is different from 0, then solutions, this symbol means exist. If I cut it, I deny it. So solutions do not exist. If you look at what we're saying here is a is 0, so in other words, this bit goes away. B is not 0, so this bit stays. So we have something like 3 equal 0. 3 would be the value of b in this particular case, equals 0. So we know that this is an absurd, it's impossible. So depending on the value of the coefficient a, and subsequently of the value of b, we could have any x as a solution or no x as a solution. So the more interesting case is if a is not 0, then what can we do? Well, if a number is not 0 for sure, we may divide or multiply the left-hand side and the right-hand side of an equation by that number. So in this case, I want to divide by that number. So I have ax plus b divided a equals 0. I can split this one in two fractions where I separate two pieces of the numerator divided by the same denominator. So I could have ax divided by a plus b divided by a equals 0. These two can be simplified. Remember, it's not 0. We have assumed it is not 0, so we can divide. And I'm left with x plus b divided a equals 0. In other words, x equal minus b divided by a. let's apply an example. So let's find an example. So if I have 3x plus 6 equals 0, I could take 6 on the, onto the right hand side. 3x equal minus 6 divided by 3, x equal minus 6 divided by 3, that is minus 2. So what are we demonstrating with this? We're demonstrating that we do have a solution, that the solution is unique, assuming a is not 0. So we are assuming we can find the solution that is unique, and we actually can find the solution. So we do have a formula. This is the formula for linear equations in one unknown. X equal minus b divided by a, where b is the constant term or the known value, and a is the coefficient of x. If a was 0, this equation would degenerate. It wouldn't really be linear anymore, because essentially the first part would go away, and we would have either an identity or an absurdity, depending on the value of b. So not really interesting in most cases, unless you actually find this after some calculations. Then you could actually draw some conclusions. But you would normally not find exercises asking you, 3 equals 0, find the solution. It doesn't make a lot of sense. It's not a lot of fun. So for degree equal 1, that means linear equations, the solution is unique, and we have a closed formula, so a well-defined formula to find it. What about if the degree is slightly higher than? So if the degree is 2, what terms can we have now? We can have something constant, something times x power 1, and something times x power 2. So if I place all the monomials that make up this polynomial in decreasing powers, so x squared, x power 1, and here there is a constant term which I will write in a moment, equal to 0. Now I can assign coefficients in the right orders in a way that is easy to remember. So a x squared plus bx plus c equals 0. This is the most generic quadratic equation, and this is obviously a simple special case of integer rational algebraic equation. So the question is that, again, have we got solutions? And if we do, is it 1? Is it 2? Is it infinite solutions? Or maybe there are no solutions at all? So the first thing to do is, let's talk about where we are looking for solutions. We are looking for solutions in our set of real numbers, which is R. However, let's remember that there is this bigger set C, which strictly contains R. So in other words, C has got anything that R has and more. The coefficients we are looking at, typically A, B, C, they all are real numbers. They belong to R. So these are either integer or maybe negative numbers. They could be natural numbers. They could be fractional numbers. They could be roots. They could be pretty much any real number we can think about. But the powers of x have an integer positive integer positive exponent, which is either 2 or 1 or none. So now we have a question then. Is there a way to find the solutions? And actually, yes, there is, and the discussion that generates is very interesting. So let's look at how we can try to find the solutions. The idea is to try to find the square development of a binomial within the left-hand side. This may not be the square of a binomial as it is, ax squared plus bx plus c, but part of it might actually be if we do some appropriate operations. Let's remember one thing though. If I have, for example, k plus t square, and I'm deliberately using different letters than this because I don't want to generate confusion. So k plus t square is the square of the first, so k square, plus the double product of the two, 2 times kt, plus the square of the second. So let's start from our equation here, ax squared plus bx plus c. First of all, if a is equal to 0, what happens? I have bx plus c because the first term goes away. Bx plus c equal to 0. And this is a linear equation. So we go back into the first case we already studied. So there is no need to develop it further. So let's assume then that a is not 0 then. Now, if we know that a is not 0, we can do plenty of things with that. We can multiply by a, we can divide by a. So I want to multiply everything that I see here on the left-hand side by a. Actually, I want to do better than that. I want to multiply by 4 times a. So 4 times a multiplied ax squared plus bx plus c equal 0. Let's develop this multiplication. So 4a squared x squared plus 4abx plus 4ac equals 0. Now, why did I do that? For 2 reasons. First of all, I wanted to have one more a here, so this one looks like a square. I'm trying to identify something that I can call k here. So as you can see, ax is something that I could call k. So why did I put a 4 here? Now, if you look at this expression, here the coefficient is 1, here is 2. How can I make up for that? Because in my particular case, I had a and b. Well, there is one number that if you multiply by itself, or if you multiply it by 2, you get the same number, and that number is 2. Well, there is also 0, but that wouldn't be very interesting. So, in other words, you may have noticed in the past that if you have, for example, this type of binomial that is, let's say I have now 2k plus t square. The square of the first is 4k squared plus the product of the two would be 2kt, but we need to take the double product. So it's 4kt and the square of the last, so plus t squared. Now, as you can see, I have the same number in here. So it is convenient to do something to do with the number 2 because then you would have an expression that looks pretty much similar to developing a square of a binomial with the 2 in here. So this one will be the square of 2ax. So here I want to recognize the double product of 2ax, so double product of 2ax and something. So what would that something be? 2 to 4x is 4ax. The only thing left is b. So there you go. This is the second part of our binomial that we want to identify. And this b will have a very similar role to what t has here. So the only problem is that to complete the square, we need to have the square of the first, and we have it, the double product of the first and the second, and we have it. Then we have to have the square of the second. We haven't got it at the moment. So let's add it. But can I add it like this without paying any toll? No, I can't. I can only do it in one or two ways. Either I add it to the left-hand side, but also to the right-hand side, or I add it to the left-hand side and I also subtract it from the left-hand side. I can do one of the two things. Let's say I will add plus b squared to the left-hand side and the right-hand side of this equation. So again, let's write 4a squared x squared plus 4abx. Let's put b squared here and then plus 4ac, and on the right hand side, as promised, we also have to add b squared. Now, of course, I could simplify this and I would go back to where I was, and it wouldn't really be very useful, but it just shows you that essentially I haven't done anything illegal here. What I have done though is that I have created an expression here that can be identified as the square of a particular binomial. This is nothing but the square of 2ax plus b. Let's verify it. Square of this, 4a squared x squared is there. Product of these, 2abx, but we need to take the double product, so 4abx is there, plus b squared is there. So plus 4ac equal b squared. Now what I want to do is to take this term to the right hand side. So we have 2ax plus b squared equal b squared minus 4ac. So here is an important consideration to make. The left hand side is a square of something. So surely this quantity will be positive, or at the very least might be zero. It can never be negative, right? So if I look at the second part of this equation at the right hand side, nobody is telling us what the sign of this thing will be. Because if b squared is very large, larger than 4ac, this will be positive. However, if it isn't large enough, this will be negative because this quantity could be negative. Of course, it depends on the signs of a and c. But if a and c have got the same sign, so plus plus or minus minus, this lot will be negative. And if it is large enough as a number, it will bring the right hand side to become a negative number. And what happens then? That I will not have solutions. So as you can see, the critical part, the discriminant part of this thinking is the sign of the right hand side. This quantity sometimes is indicated as delta. So this delta, also called discriminant, some people call it also determinant. This delta is crucial to understand whether I have solutions or not as real numbers and whether these solutions are the same or different. So if delta is a positive number, what happens? Now it's time to erase the whole board. And just rewriting what we have written last. So 2ax plus b squared equal b squared minus 4ac, which is delta. So case 1, delta is positive. So what can I do now? I can take the square root of both sides. Remember though, if I have 9 x squared, for example, equal 9, a child would be tempted to say that, okay, a child who has studied square roots anyway, would be tempted to say that this means x equal 3. And that is not wrong, but it's only part of the truth. We have to remember that when you take a square root of a positive number, you get two possible values. And these numbers are plus or minus 3. Obviously, the same could be said from the other side as well, but you would have 4 possible cases. You would equate plus with plus, plus with minus, minus with plus, minus with minus. You would have 4 possible cases, but essentially they boil down to 2 different cases. Either these two have got, one has got sign plus and the other minus, or they got the same sign. So for example, plus and plus. So what that means is that when I take the square root of the first member of the left hand side and of the right hand side, I have to additionally count for 2 possible values. So when I take the square root, I obtain 2ax plus b equal plus or minus square root of delta. So if I bring b to the other side, I have 2ax equal minus b plus or minus square root of delta. And if I divide by 2a, remember a is different from 0 in this particular case, so if I divide by 2a, x is minus b plus or minus square root of delta divided by 2a. So these are the two specific solutions. Remember, delta is this number, b squared minus 4ac. So for example, if you have this equation, x squared minus 4x plus 3 equal to 0, I could calculate x as minus b, which is 4 plus or minus square root of delta is b square, b is minus 4, square is plus 16, minus 4 times, I'm reading here, 4 times AC. A is 1 and C is 3. So minus 4 times 3 divided by 2 times A, and A is 1 in this case. This is 4 plus or minus 16 minus 12 is 4, and the square root is 2. So 4 plus or minus 2 divided by 2. That means 4, now I have to take the two different cases. So 4 plus 2 is 6, divided by 2 is 3. 4 minus 2 is 2, divided by 2 is 1. And these are the two possible real solutions. Case 2, if delta is equal to 0, that means b squared minus 4ac is 0. Now what happens is that the thinking is exactly the same as before, but when I take the square root of 0, remember delta is 0 here, square root of 0, whether I give it a plus or a minus sign, it doesn't matter, it's the same value. So x1 or 2 is minus b plus or minus 0 divided by 2a. That means minus b plus or minus 0 doesn't make a difference. It's still minus b, doesn't change the value, divided by 2a. So what is the most interesting thing I notice in this case? That x1 and 2 are actually the same value, because there is a unique value here. For example, if I have x squared minus 4x plus 4 equal to 0, let's calculate delta right away. Delta is b squared minus 4ac. b squared is minus 4 power 2, so it's plus 16 minus 4 times ac. A is 1, c is 4. 16 minus 16 is 0. So x1 and 2 is minus b is minus 4 divided 2 times a is 1, 2, 1. On numerator we have 4, denominator we have 2, 2. And what we can say as well is that in this case, when delta is equal to 0, the quadratic equation actually has got on the left hand side the square of a binomial. If you look at this carefully, this is x minus 2 square. So essentially, the only way to get the left hand side to have value 0 is to give x the value of 2. In this particular case, if I go back on case 1 for a moment, we had found the solutions 1 and 3. So the way to simplify the equation is a times x minus 1 x minus 3 equal to 0. A in this particular case was 1, so can ignore this. So essentially the solutions were 1 and 3. So when do I have a product of two numbers equal to 0? When either this is 0 or that is 0. So when x minus 1 is 0, that means when x is 1, and it's true. Or when this is 0, that means x is 3, and that was true. In this case, instead, is the same value. Last case, delta is negative. So in this case, when I try to extract square root of delta, this, I would be tempted to say, doesn't exist. Let's try to keep our mind a little bit more open in this case. Let's say that square root of a negative number exists, but is a complex number. And it's a specifically complex number that is not a real number, we need to remember that complex numbers might also be real because the C set includes the R set. If I want to be specific and say that it is a complex number and is not real, I can use the difference between sets. So C minus R. So this number is complex, not real. And what that means is that when I extract the value of the square root, I would have to deal with complex numbers, which we will cover in the next session.